In this video, we'll be covering some of the basics of passive load pull, including harmonic tuning. To perform the measurements, we will use a technique which utilizes the receivers of a network analyzer. Now, to tune the impedances, we will use a wideband fundamental tuner on the input and a multi-harmonic tuner on the output. The S parameters of an active device provide some insight on how a device will operate at low power and at 50 ohms, also known as small signal behavior. A load pull system actually tunes to non-50 ohm impedances and reports measurement parameters in its large signal state. As the first step, we will perform a peak search on the source of the device to determine the optimum impedance for delivered power. The software's algorithm varies the input impedance until it finds the optimum point for the measured parameter at a fixed power level. We then perform the same algorithm on the output, but this time for gain or output power. This will help us determine our match at small signal and serve as a starting point before we move on to large signal measurements. In this next step, we want to determine the 1 dB compression point of the device. An amplifier maintains a constant gain for low-level input signals. However, at higher input levels, the amplifier goes into saturation and its gain decreases. The 1 dB compression point, P1 dB, indicates the power level that causes the gain to drop by 1 dB from its small signal value. When operating a device at a certain compression point, the small signal match will most likely be different. We have different options at this point. We can perform another peak search to see if our optimum output match has changed, or we can perform a fundamental load pull and record output power from multiple impedances and plot these contours to get more insight on how the device performs versus load impedance. In this example, the harmonic impedances vary as we change the input impedance. Later, we will show how controlling the harmonic impedances allowed you to optimize parameters like efficiency or linearity. Output power is only one parameter RF designers use to optimize their devices. Power added efficiency, EVM, ACPR are as important. Here we are plotting output power and efficiency for multiple impedances, and as expected, the optimal impedances for both parameters do not coincide. With this information, the designer can select an optimum impedance for output power, efficiency, or select an intermediate impedance where both output power and efficiency are interesting. The final step will be to determine the optimum harmonic impedance. So far, when changing the fundamental impedance, the harmonic impedances were recorded but not controlled. By maintaining fundamental impedance constant and sweeping the second harmonic, we will see a change in power added efficiency. The goal here is not to match the harmonic impedance as we did at the fundamental, but to reflect the harmonic power back to the device at a certain phase and see the variation in efficiency. A few points of power added efficiency can have a huge impact on a design. As we can see in this example, we can have a drop of up to 10% efficiency by simply choosing the wrong harmonic impedance in our design. Only a harmonic load pull system can provide this level of information and help designers make the right choice. For more information, please contact us. Thanks for watching.